Dear students, after studying this module, you shall be able to know the fragmentation in mass spectrum, learn site of cleavage for different types of molecules and classes of compounds, identify the types of fragments generated for different functional groups and various compounds, evaluate peaks in mass spectrum and analyze any mass spectrum of a given organic compound. Now students, let us begin with the introduction of the fragmentation in various classes of organic compounds. First of all, the mass spectrum of organic molecules contains various fragment peaks in addition to the molecular ion peak. The fragment observed for a particular class of compounds have similar features. Now we are going to come up to the various classes of compounds and their fragment patterns. Let us now begin first of all with the alkanes. The mass spectra of alkanes is very predictable and the stability of carbocations or the radicals formed is used to predict or explain the observation of the fragments which are formed. Method of fragmentation is single bond cleavage in most cases. The molecular ion peak is strong for lower N alkanes, but its intensity falls with the increase in size and branching of the alkanes. A regular series of fragment peaks separated by 14 AMU are observed in case of alkanes. There is a loss of CH2 units in series M-14, M-28 and M-42 etc. so on. Now you can clearly see this in the mass spectrum of butane. We have shown you the fragments and the molecular ion peak. As the carbon skeleton becomes more and more branched, the intensity of molecular ion peak generally decreases. Branched chain alkane ruptures at the point of branching. Formation of tertiary carbocation or carbocation radical is favored over secondary over primary radical cations. Now if you remember, in the past modules we have taught you about the Stephenson's rule. This is because of Stephenson's rule. The tertiary formation, the tertiary carbocation radical cation is favored over the secondary and secondary is favored over the primary. As seen in isooctane students, the molecular ion peak is very weak because it is preferred to form a fragment rather than give a molecular ion peak. Now you can see the mass spectrum of isooctane with a weak molecular ion peak and a good intensity fragment peak. Dear students, now we will take up cycloalkanes and their fragmentation patterns. Cycloalkanes generally form strong molecular ion peaks. Fragmentation via the loss of molecule of ethene, that is M, the molecular mass minus 28, is common either from the parent molecule or the intermediate OE plus, that is the odd electron cation. Fragmentation of ring compounds requires the cleavage of two carbon-carbon bonds, which is a much difficult process than the cleavage of one bond such as in alkanes. Therefore, a larger proportion of cycloalkane molecules than that of cyclic alkane molecules survives electron bombardment without undergoing any sort of fragmentation. Now let us talk of alkenes. Electron bombardment removes one of the electrons in the pi bond, leaving the carbon skeleton relatively undisturbed. The alkenes have a distinct molecular ion peak, which should correspond to a molecular formula with the double bond equivalent of at least 1. Commonly fragmentation occurs to favor the allyl cation with a M/Z value of 41 and its formation. The general formula of such a fragment in alkenes is CnH2n plus and CnH2n-1 plus, that is both of these cations. It is sometimes difficult to locate double bonds in alkenes since they migrate very readily. Now for an example here, we have taken the mass spectrum of butene. Now you can see the distinct molecular ion peak at 56 followed by its fragmentation peak. Now let us talk about cycloalkenes, that is cyclic alkenes. The mass spectra of cycloalkenes shows quite distinct molecular ion peaks For many cycloalkenes, migration of double bonds gives virtually the identical spectra. Cycloalkenes do have a characteristic fragmentation pattern that corresponds to the retro-Diels-Alder reaction, as we have talked of many times in the previous module when we were discussing the different types of fragmentation generally in various functional groups. Now, let us come to the talking about alkynes. The molecular ion peak here is again very intense like alkenes. As such, there is no simple fragmentation observed for alkynes, but a lot of complex molecules can be also studied like the fragmentation pattern of alkynes. Now, here we have taken the example of one pentyne and its mass spectrum. Here you can see a peak for propargyl ion having a M by Z value of 39. Terminal ion also undergoes loss of terminal hydrogen to give you a M-1 peak, student, because that hydrogen is very acidic. So, you observe a M-1 peak, so it can be easily removed. The M-1 peak in pentyne appears at M by Z value of 67. Now, you can see an intense molecular ion peak here in the mass spectrum of one pentyne as is shown in the figure, followed by the M-1 peak and followed by its fragment peaks. Now, students, let us come to the brief discussion of aromatic hydrocarbons. The mass spectrum has an intense molecular ion peak. Fragmentation of benzene is not observed significantly. As you know, it requires a great deal of energy because benzene is a very stable system in itself. Now, you can see here, you can only see the mass spectrum of benzene and you can only see here the molecular ion peak which appears at 78. Now, considering alkyl benzenes, side chain containing aromatic molecules undergo fragmentation to form benzyl cation, which rearranges to form tropylium ion, as you know, which is again aromatic with the M by Z value of 91 for the molecular formula C7H7 plus. The M by Z value of 91 ion is subsequently expels out acetylene, that is C2H2, to give a M by Z peak at 65. The tropylium ion can fragment further to form cyclopentadienyl cation, which is again aromatic, which in turn can again fragment to form another equivalent of ethyne and the aromatic cyclopentadienyl cation with the M by Z value of 39. Now, considering the mass spectra of ortho, para and meta disubstituted aromatic rings. The mass spectra of ortho, meta and para disubstituted rings are essentially identical. As a result of this fact, substitution pattern in polyalkylated benzenes cannot be determined by mass spectrometry. Now, we move on to the discussion of alcohols and phenols. The molecular ion peak generally less intense for primary and secondary alcohols. The molecular ion peak may be absent in tertiary alcohols, students, because you know that in tertiary alcohols it is preferred that the tertiary carbocation loses itself, and because it is more stable than primary and secondary. The fragments are formed by the loss of alkyl group or water molecule. That means it will give a peak at M-18 and an alpha cleavage adjacent to the hydroxyl group. The molecular ion peak in 1-butanol, 2-butanol and tertiary butanol at M by Z is equal to 74 are very weak, too weak to be detected and absent respectively, because of the reasons already told that tertiary butanol it will prefer to be fragmented than secondary than the primary one. During the fragmentation of these alcohols, the larger alkyl group is generally lost, and this is due to the Stevenson's rule, as has been explained to you students in the previous modules. Now, here you can see this in a reaction, the loss of the larger alkyl group is preferred. Now, students, as we have talked about the dehydration in case of alcohols, which gives rise to a peak of M-18, dehydration may occur by either thermal dehydration prior to ionization or by fragmentation of the molecular ion itself. Thermal dehydration is especially troublesome for alcohol samples analyzed by GCMS. The injection port of the gas chromatograph is usually maintained at more than 200 degrees Celsius, and many alcohols, especially tertiary or allylic benzylic alcohols, will dehydrate before the sample molecules even reach the GC column, and certainly before the molecules reach the ion source of the mass spectrometer. Thermal dehydration is a 1-2 elimination of the water molecule. If the alcohol molecules reach the ion source intact, however, dehydration of the molecular ion can still occur at that point, but in this case it is a 1-4 elimination of water via a cyclic mechanism involving a transition state. Alcohols which contain 4 or more carbon atoms may undergo simultaneous loss of both water and ethylene molecule. This type of fragmentation is not prominent for 1-butanol, but is definitely responsible for the base peak at the value of m by z is equal to 42 in the mass spectrum of 1-pentanol. Now students, here you can see the mass spectrum of 1-butanol. Clearly you can see the molecular ion peak followed by the various fragments which are obtained. Cyclic alcohols may undergo fragmentation by at least 3 different pathways. Now let us discuss them one by one. The first fragmentation is simply the alpha cleavage and the loss of hydrogen atom because it is acidic to yield an m-1 fragment. The second fragmentation path begins with an alpha cleavage of the ring bond adjacent to the hydroxyl bearing carbon, followed by a 1,5 hydrogen migration. This moves the radical site back to a resonance stabilized position adjacent to the oxonium ion which is formed. A second alpha cleavage now takes place and which results in the loss of a propyl radical and formation of a protonated acrolein ion with m by z value of 57. The third fragmentation path of cyclic alcohols is dehydration via the abstraction of a hydrogen atom from a 3 or 4 carbon atoms away, that is the hydrogen atom is transferred in a 5 or a 6 member transition state to produce a bicyclic radical cation with a m by z value of 82. Simple phenols. Now let us discuss about these simple phenols. Simple phenols give intense molecular ion peaks. The common fragmentation involves the loss of carbon monoxide having a molecular weight of 28. Thus, you will observe a peak at m-28 and CHO, that is loss of m-29. Phenols with alkyl side chains undergo cleavage at benzylic bond leading to the formation of hydroxytropylium ion. Now students, after having discussed in detail alcohols and phenols, we are moving on to the discussion of ethers. Aliphatic ethers exhibit weak but observable molecular ion peaks. Fragmentation includes alpha cleavage, that is we will have fragments at m by z value of 43, 59, 73 etc. Or you can say we will have m-31 peaks, m-45 peaks and m-59 peaks etc. Formation of carbocation fragments and loss of alkoxy group, that is we can say inductive beta cleavage. A third type of fragmentation occurs as a rearrangement reaction of one of the fragment ions rather than the molecular ion itself. The rearrangement involves transfer of a hydrogen which is beta to the oxonium ion with concurrent formation of an alkene. This type of rearrangement, students, is particularly favored when the alpha carbon of the ether is particularly branched. The mass spectrum of diisopropyl ether has a peak with the m by z value of 87 due to the alpha cleavage. The carbon oxygen cleavage of ether yields a cation having a molecular formula C3H7 plus at a m by z value of 43. Now, you can observe this clearly in the mass spectrum of diisopropyl ether, where you can see it has a small but a clear molecular ion peak followed by the various fragments, and a fragment at 43 is very clearly seen here. Methyl phenyl ethers, that is aromatic ethers, they undergo fragmentation at their CO bonds with the loss of CHO. That means M-30 molecular ion peak you will be observing, and a loss of CH3, that is M-15 peak will be also observed. Acetals and ketals behave very similar to ethers, that is why we have them discussion under the topic of ethers. However, students, fragmentation is even more favorable in case of acetals and ketals than in ethers. So, the molecular ion peak of an acetal or a ketal may either be weak or may be totally absent, because in that fragmentation is very much favored. Now, coming to the brief discussion of aromatic ethers again. Aromatic ethers, except for methyl phenyl ethers as discussed above, fragment by transfer of beta hydrogen to give a peak at the M by Z value of 94, which expels carbon monoxide to give a peak at M by Z value of 66. Now, we have now to discuss the aldehydes as functional groups. The molecular ion peak of aldehydes is observable, but usually it is fairly weak. That means you are having an M by Z peak at 29 and 44 for aliphatic aldehydes, while aryl aldehydes, that means aromatic aldehydes, give a strong molecular ion peak. The fragmentation includes alpha and beta cleavages, both of them. However, if we have a gamma hydrogen present, then the very famous McLafferty rearrangement, as referred to in many other previous modules, has been discussed, is also observed in case of gamma hydrogen's presence. For aromatic aldehyde students, molecular ion peak is very strong. That means you are going to have a peak at M-1 and M-29, because as we have discussed, the M by Z at 29 and 44 will be there. So, you can see here the fragmentation reactions of various aromatic aldehydes in these two reactions over here, where you have the M-1 peak and the M-29 peak, and very visible in the reactions. Now, coming to the discussion of alpha cleavage. Alpha cleavage occurs very commonly, and the peak due to the loss of one hydrogen atom is very characteristic of aldehydes. The characteristic peak due to HCO plus observed at M by Z 29 is very commonly observed in case of aldehydes. Now, during beta fragmentation, the peak at M-43 is also observed if beta cleavage takes place. Now, you can see here the various reactions which are involved in the fragmentation in case of beta cleavage, and you can also see clearly the mass spectrum of butanol, that is the aldehyde, with the molecular ion peak clear, as well as the various fragment ions with the clearly M by Z values placed. Now, students, let us discuss briefly about aromatic aldehydes. The aromatic aldehydes also exhibit intense molecular ion peaks, and the loss of one hydrogen here is also very common via alpha cleavage. The resulting M-1 peak may in some cases be more intense than the molecular ion peak itself. Again, here students, you should note that the hydrogen here is very acidic, that is why you have a M-1 peak. Note that the peak at M by Z is equal to 77 corresponds to the phenyl cation, which is formed by the loss of formyl cation from aromatic aldehydes. Now, let us continue our discussion with carbonyl groups. Now, we will move our discussion from aldehydes to ketones. Ketones show an intense molecular ion peak, again just like aldehydes. During fragmentation, alkyl group next to the carbonyl is lost. More likely, the larger alkyl group is lost. Again, here you can see the importance of Stephenson's rule, as has been explained to you in the previous module. and followed by the common formation of RCO plus just as in case of aldehydes. The larger of the two alkyl groups attached to the carbonyl group appears more likely to be lost, in keeping with the Stephenson's rule. Now you can see the reactions involved in the fragmentation of ketones over here. For aliphatic ketone students, the fragmentation pattern shows peaks at M-15, M-29 and M-43. Now you can clearly see this here in the case of mass spectrum of butanone. You can see the molecular ion peak followed by its fragment ion peaks. If gamma hydrogen is present, then McLafferty rearrangement is definitely possible, and you can see this here where gamma hydrogen is present in case of this ketone, and how the McLafferty rearrangement takes place to form these particular species, and these fragments are also observed in the mass spectrum. Cyclic ketones undergo fragmentation and rearrangement in many various ways. Cyclohexanone, for example, gives a molecular ion peak at M/Z value of 98. Fragmentation and rearrangement in case of cyclohexanone gives a peak at M/Z 83, 70, 55 and 42, etc. Now various reactions which are included in case of ketones and formation of fragments are shown here. Now aromatic ketone students may undergo alpha cleavage to lose the alkyl group and form the phenylacylium ion, that is with the molecular formula C6H5CO plus and the M/Z value 105. This ion can undergo secondary fragmentation to lose carbon monoxide, forming the C6H5 plus ion at an M/Z value of 77. Aromatic ketone students also may undergo McLafferty rearrangement. Now how the McLafferty rearrangement takes place is shown here in this reaction. As you can see here, the clearly taking place of McLafferty rearrangement and the formation of fragments henceforth. Now let us move our discussion to discussion of another functional group, that is another carbonyl group, esters. Weak molecular ion peaks are observed in mass spectrum for esters as they readily undergo fragmentation, but it is usually possible to observe weak molecular ion peaks in the mass spectra of methyl esters. The esters from higher alcohols form much weaker molecular ion peaks as in the mass spectra of methyl esters. Esters of alcohols larger than 4 carbons may form molecular ion peaks that fragment quickly, that means too quickly to be observed. Alpha cleavage involves the loss of alkoxy group to form acylium ion, which gives rise to peaks at M-31, M-45 and M-73. Methyl esters having a gamma hydrogen undergo beta cleavage via the McLafferty rearrangement, producing a peak at M/Z value of 74. Ethyl, propyl, butyl and higher alkyl esters also undergo alpha cleavage. In addition, however, these esters may undergo an additional rearrangement of the alkoxy portion of the esters that results in fragments that appear in the series with the M/Z value of 61, 75, 89 and so on. Coming to the discussion of benzyl esters. Benzyl esters undergo rearrangement to eliminate a neutral ketene molecule and the radical cation of benzyl alcohol, that is at the M/Z value of 108. The resulting ion is often the most intense peak in the mass spectrum of such a compound. Alkyl benzoate esters prefer to lose the alkoxy group to form the C6H5CO plus ion and the M/Z value of 105. This ion may lose carbon and carbon monoxide to form the phenyl cation, that is C6H5 plus at M/Z is equal to 77. Alkyl substitution on benzoate esters generally appears to have little effect on the mass spectral results unless the alkyl group is in the ortho position, with respect to the ester functionality. In this case, the alkyl group can actually interact with the ester functional group with the elimination of a molecule of alcohol. Now, here you can see the mass spectrum of ethyl butyrate, and you can see the molecular ion peak and its fragments. And you can also see here how the fragmentation in case of esters is taking place. Now, we will move our discussion to carboxylic acids. Aliphatic carboxylic acids have weak but still the observable molecular ion peaks with M-17 and M-45 peaks also. Aromatic carboxylic acids show strong molecular ion peaks. In short chain acids, alpha cleavage on the either side of carbonyl group leads to the loss of OH and COH moieties. The M by Z peak at 45 is due to the loss of COOH plus ion. Now, here you can observe these fragments and the molecular ions in case of the mass spectrum of propionic acid, that is a 3 carbon acid. Acids containing gamma hydrogen undergo McLafferty rearrangements. In case of carboxylic acids, this rearrangement produces a prominent peak at M by Z equal to 60. Here you can see the McLafferty rearrangement in case of acids containing the gamma hydrogen. In aromatic carboxylic acid students, the OH loss produces a peak at C6H5CO plus ion with the M by Z value of 105, followed by the loss of carbon monoxide to give a C6H5 plus ion with the M by Z value of 77. Now, having finished the discussion of carboxylic acids, both aliphatic and aromatic, we now move our discussion from the carbonyl group containing functionalities to amines. A compound with odd number of nitrogen atoms has odd numbered molecular weight, and with even number of nitrogen atoms has the even molecular weight. This is the nitrogen rule. Thus, the nitrogen rule is very important in determining whether a compound contains nitrogen or not. In aliphatic amines, the molecular ion peak may be very weak or even absent. Thus, what is the most intense peak? The most intense peak in case of amines is the peak due to the alpha cleavage. During loss of the alkyl group, a larger group is always preferably lost, obviously due to the Stevenson's rule. As you can see here, the loss of the fragments in case of amines. Why the molecular ion peak is not observed? Because a peak at M by Z 30 is observed for a primary peak due to the alpha cleavage for CH2 double bond NH2 plus ion, which is formed by the expulsion of a radical from the molecular ion peak. That is why the molecular ion peak is absent in generally in case of amines. Now, students, here you can see it in the mass spectrum of ethylamine how the fragments and the very faint molecular ion peak is there, or sometimes it may be absent also. The presence of a peak is strong, although not conclusive evidence that the test substance is a primary amine. The peak may arise from secondary fragmentation of ions formed from the fragmentation of secondary or tertiary amines as well. The same beta cleavage peak can also occur for long chain primary amines. Further, fragmentation of the R group, that is the alkyl group of the amine, leads to a cluster of fragments which are 14 mass units apart from each other due to the sequential loss of the CH2 units from the R alkyl group. Long chain primary amines can also undergo fragmentation via this same process. This is particularly favorable when N is equal to 4, since a stable 6-membered ring results. Again, here you can see the importance of bare strain theory, because a stable ring formed will give you that particular fragment. In this case, if fragment appears at M by Z value of 86, secondary or tertiary amines may also undergo fragmentation processes as described earlier. The most important fragmentation here is thus the beta cleavage. Let us now discuss about cyclic aliphatic amines. These usually produce intense molecular ion peaks as reverse to the normal aliphatic amines. And the main modes of fragmentation are basically drawn here, and you can see them in the figure. Let us move our discussion of amines from normal aliphatic amines to cyclic aliphatic amines and now to the aromatic amines. Aromatic amines show intense molecular ion peaks, again which is reverse to the normal aliphatic amines. A moderately intense peak may appear at a m by z value 1 mass unit less than that of the molecular ion due to loss of a hydrogen atom. The fragmentation of aromatic amines can be illustrated in the case of aniline here. You can see this clearly in the reactions drawn. Very intense molecular ion peaks generally characterize substituted pyridines. Frequently, loss of a hydrogen atom to produce a peak at a m by z value 1 unit mass less than the molecular ion peak is also observed. When the alkyl side chain attached to the pyridine ring contains 3 or more carbon atoms linearly, then obviously McLafferty rearrangement is also preferred and will also occur. The mode of cleavage is most important for substituents attached to the number 2 position in case of the pyridine ring. Now we move our study of the nitrogen compounds to some selected nitrogen and sulfur compound students. As is true for amines, nitrogen bearing compounds such as amides, nitriles and nitro compounds must also follow the nitrogen rule. So as per this, first of all we would like to discuss with you the functional group amides. Molecular ion peak is usually observable. Primary amide have a fragment ion peak at m by z value of 44, mainly due to beta cleavage and loss of alkyl group. Now here we have shown you some reactions where it is clearly visible how beta cleavage takes place and how a m by z value of 44 appears. If gamma hydrogen is present, then amides obviously undergo McLafferty rearrangement. Primary amides have a peak at m by z value of 59. For in the case of N-alkyl amides, analogous peaks at m by z values of 73, 87, 101, so on often appear. Let us now move our discussion to another nitrogen containing compound class of functional groups, that is nitriles. Aliphatic nitriles usually undergo fragmentation so readily that the molecular ion peak is too weak to be observed, just as you remember in case of aliphatic amines. However, most nitriles form a peak due to the loss of one hydrogen atom, producing an ion of the type RCH double bond C double bond N cation. Although this peak may be weak, but it is useful as a diagnostic peak, especially for characterizing the nitriles. When the alkyl group attached to the nitrile functional group is a propyl group or some longer group, the most intense peak in the mass spectrum results from a McLafferty rearrangement. So now students, you know more than 4 carbons if they are present with any functional group, then McLafferty rearrangement is bound to happen and you will observe the fragments according to this rearrangement. With high molecular weight nitriles, most of the fragment ions of mass 41 are C3H5 plus ions rather than ions formed as a result of the McLafferty rearrangement. The strongest peak in the mass spectrum of an aromatic nitrile is the molecular ion peak itself. More importantly, fragmentation involves the loss of HCN molecule, that is the hydrogen cyanide molecule. Now we will move on to the discussion of thiols and thioethers. Now as you know students, we use the term thio for anywhere where the atom sulfur is involved. Thiols show molecular ion peaks that are more intense than those of the corresponding alcohols, that means alcohols containing the oxygen atoms. A characteristic feature of the mass spectra of sulfur compounds is the presence of a significant M+2 peak. This peak arises from the presence of a heavy isotope, that is 34 sulfur, which has a natural abundance of 4.4%. Although the abundance is low, but still this peak is observed. The fragmentation of thiols are very similar to those of the alcohols. As alcohols tend to undergo dehydration under some conditions, as explained previously in this module, thiols also tend to lose elements of hydrogen sulfide likewise, giving rise to a peak at M-34. Thioethers on the other hand show mass spectral patterns that are very similar to those of ethers. As in the case of thiols, thioethers show molecular ion peaks that tend to be more intense than those of the corresponding ether. Nitro compounds. The molecular ion peak for aliphatic nitro compounds is generally not observed, while for aromatic nitro compounds the molecular ion peak is very strong. For aliphatic nitro compounds, a peak at M by Z is equal to 30, which corresponds to NO plus ion, that is nitronium ion, and M by Z at 46, that corresponds to NO2 plus ion, is observed. Now you can see here the mass spectrum of 1-nitropropane and a very faint, you can see a molecular ion peak. However, the fragments are very intense as discussed above. Now students, let us discuss about alkyl halides. Aliphatic halides have molecular ion peaks stronger for iodides, less strong for bromides, weak for chlorides and weakest for fluorides. Alkyl chloride and bromide have M+2 peaks due to the presence of isotopic forms of bromine and chlorine. From the natural abundance of isotopes of chlorine, one can generally conclude that if the M+2 peak is 1/3 the height of the molecular ion peak observed, then the compound contains one chlorine atom, because the natural abundance of chlorine 37 is 1/3 that of 35 chlorine. Now chlorine comprises of two isotopes. The isotope with greater abundance has a mass of 35 AMU and the relative abundance of 35 AMU chlorine is 75.77%, and the one with a minor abundance has a relative mass of 37 AMU and it has a relative abundance of 24.23%. If the M and M+2 peaks are about the same height, then the compound contains one bromine atom, because the natural abundances of 79 bromine and 81 bromine are about the same. Now bromine has a nearly 50-50 mixture of isotopes having atomic masses 79 with a relative abundance of 50.69%, and the 81 bromine AMU, that means the mass of bromine 81 is 81 AMU and the relative abundance is equal to 49.31% respectively. Now students, you can see here the mass spectrum of bromohexane, and you can see there are two peaks, that is M and M+2, and their relative intensities are the same because of the equal isotopic ratios of 79 and 81 bromine. Alkyl halides may also lose a molecule of HX according to the process which is shown here. A mode of fragmentation is most important for alkyl fluorides and chlorides and less important for bromides and iodides. A less important mode of fragmentation is alpha cleavage, for which a fragmentation mechanism may be, and you can see here the mode of fragmentation we have given. When the alpha position is branched, the heaviest alkyl group attached to the alpha carbon is lost with greatest facility. The peaks arising from alpha cleavage are usually rather weak. A fourth fragmentation mechanism involves rearrangement and a loss of alkyl radical, and you can see that in the reaction that we have put. The corresponding cyclic ion can only be observed at M by Z 135 and M by Z 137 in the mass spectrum of 1 bromohexane, and at M by Z 105 and 107 in the mass spectrum of 2-chloroheptane. Such fragmentation is important only in the mass spectra of long chain alkyl chlorides and bromides. The molecular ion peaks in the mass spectra of benzyl halides are usually of sufficient intensity to be observed. The most important fragmentation involves the loss of halogen to form C7H7 plus cation, when the aromatic ring of benzyl halide carries substituents. A substituted phenyl cation may also appear in the mass spectrum. The molecular ion peak of an aromatic halide is generally quite intense, and the most important mode of fragmentation involves the loss of halogen to form the C6H5 cation. Now students, let us summarize this module. The mass spectra of alkanes is very predictable, and the stability of carbocations or radicals formed is used to predict or explain the observation of the fragments henceforth obtained. As the carbon skeleton becomes more branched, the intensity of molecular ion peak decreases in alkanes. Commonly, fragmentation in alkenes occurs to favor the allyl cation with the M by Z value at 41 and its formation. Alkyl benzenes undergo fragmentation to form benzyl cation, which rearranges to form tropylium ion with the M by Z value of 91 and a molecular formula of C7H7 plus. The molecular ion peak generally is less intense for primary and secondary alcohols. The molecular ion peak may be absent in case of tertiary alcohols due to more favored fragmentation pattern. Aliphatic ethers exhibit weak but observable molecular ion peaks. Fragmentation includes alpha cleavage. M by Z values are 43, 59, 73, etc. Or you can say M minus 31, M minus 45 and M minus 59 with the formation of carbocation fragments and loss of alkoxy group. The molecular ion peak is observable but usually fairly weak, with the M by Z value is equal to 29 and 44 for aliphatic aldehydes, while for aryl aldehydes they give a strong molecular ion peak. The fragmentation includes alpha and beta cleavage. If the gamma hydrogen is present, then we already told you that McLafferty rearrangement is also observed and is preferred. Ketones show an intense molecular ion peak. During fragmentation, alkyl group next to the carbonyl is lost. More likely, the larger alkyl group is lost, in keeping with the Stephenson's rule, with formation of RCO plus cation. If gamma hydrogen is present, again students, McLafferty rearrangement is possible. We then talked of weak molecular ions being observed in mass spectrum of esters as they readily undergo fragmentation. Aliphatic carboxylic acids were next, and we have told you that they have weak but observable molecular ion peaks, with M minus 17 and M minus 45 peaks being observed. Aromatic carboxylic acids show strong molecular ion peaks. A compound with odd number of nitrogen atoms has an odd number of molecular weight, and even numbered nitrogen atoms has an even numbered molecular weight. This is the nitrogen rule. In aliphatic amines, the molecular ion peak may be very weak or even absent. The most intense peak is due to the alpha cleavage, but this is not the case for aromatic amines. We have also discussed the other nitrogen containing compounds like amides, nitriles, etc. The molecular ion peak is usually observed in case of primary amide with a weak fragment ion peak at a M by Z value of 44 due to alpha cleavage and loss of the alkyl group. However, for the molecular ion peak of aliphatic nitro compound is generally not observed, while for aromatic nitro compounds the molecular ion peak is strong. Moving on, we studied about aliphatic halides. Aliphatic halides have a strong molecular ion peak for irides, then bromides, then chlorides, and weakest for fluorides. Alkyl chlorides and bromides have M+2 peaks due to presence of two isotopic forms of bromine and chlorine alike, and their intensities are 1/3 for chlorine and 50-50% for bromine. Now students, I think this module must have been very informative for you, as it has told you about the mass spectrum and the fragmentation patterns of almost all the functional groups which are involved in all the organic compounds that we study.